This is section 11.7, part 2, and we're going to start looking at a few examples of projectile motion problems. So in example 2, we're told that a rock is thrown from a height of 40 feet at an angle of 45 degrees above the horizontal with initial speed 10 square root 2 feet per second. The first thing we're asked for are the equations of motion, and anytime you're asked for that, we're referring to r, the position, v, the velocity, and a, the acceleration. So let's start with a little diagram. We are told that the rock is initially thrown from a height of 40 feet. I'll typically start on the x-axis to say that the initial position then is 0 in the x direction and 40 in the y direction. So 0, 40 would be that initial position vector. Remember, that's in our process what we were calling x naught, y naught. All right, the trajectory then is going to go slightly upward and then out and eventually land on the ground. Excuse me. And we were also told something about the initial position vector. It's thrown at an angle of 45 degrees above the horizontal. So if this is the horizontal, right where that rock is, the velocity vector tangent to the curve is at a 45-degree angle to that. And the speed is 10 square root 2. So the magnitude of this vector is 10 square root 2. And that means I could write the vector itself as 10 square root 2 cos 45 degrees and then 10 square root 2 sine 45 degrees. Since both cosine and sine of 45 degrees are square root 2 over 2, that's going to give me 10 times 2 is 20, divided by 2 is 10. And that'll be the same for the y component. So 10, 10 is the initial velocity vector. And in our process, that's what we were calling u naught and v naught. So now that I've got all of my constants defined, oh, actually, I should probably say one more thing. G in this case, since we're looking at units of feet per second, I'll use the American system here and say G is 32 feet per second squared. All right, so at this point, to write the R equation, I'm just going to substitute all of these values into the R equation that we derived in the last video. So R will be, actually I'll just write it out first. And in this case, that's going to give me 10t plus x naught is actually just 0, so I'll leave that off. And then negative 1/2 g, that will be negative 16 t squared, plus v naught t would be 10t, plus y naught, which is 40. So there's my first equation of motion, the R equation. We will continue. Velocity is just the derivative of R. So that's going to be 10, negative 32t plus 10. And then finally, acceleration is the second derivative. So 0, negative 32. And that one, of course, is not a surprise. That's just our acceleration of gravity, which, if that's the only force, and it has to be for the problems we're doing so far, really had to come out that way. Just seeing the gravitational acceleration. So there we go. There are our 3 equations of motion. Part B just wants the position, velocity, speed, and acceleration at a specific time, t equal 1 second. So I'm going to start plugging in t equal 1. R of 1 is going to be 10 times 1, and then negative 16 times 1 squared, plus 10 times 1 plus 40, which is 10. Let's see, 50 minus 16 would be 34. Same idea, V of 1. Plugging 10 in here, we get 10. Not 10, excuse me, plugging 1 in here. Negative 32 times 1 plus 10. And that's going to be 10, negative 22. So notice, at this point, velocity is still to the right but down. So we must be past the vertex here and on our way down. A of 1. A actually doesn't depend on time at all. Acceleration is always the same. So that's just 0, negative 32. And then finally we wanted speed. Speed is the magnitude of the velocity vector. So in this case, that would be the square root of 10 squared plus negative 22 squared. Which is about 24.17. The exact value was actually the square root of 584. All right, the next problem asks us to find the time of flight and then the velocity at impact. So again, the time of flight means when does this rock land? And just like when we did this problem in the one-dimensional situation, the rock's going to land when it hits the ground, which is when the height is 0. In this case, if we think back to our original position function, the x component doesn't tell us anything about when the rock lands. It's the y component, right? When the y component is 0, we will be here on the ground. Whatever the x is, but y equals 0. So, really this just amounts to setting the y value equal to 0. Or, in this case, negative 16t squared plus 10t plus 40 equals 0. And again, like I said last time, you are welcome to use whatever means you want to solve that. I do have that little app, the PolySci, which makes it simple, but you can use a quadratic formula, you can graph it, you can do anything you want. Let's see, negative 16, 10, and 40 are my coefficients. And it looks like my t-values are 1.924 and negative 1.299. In these applications, since we're starting at t equals 0, any negative value of t refers to a time before we ever threw the projectile. So not realistic. Our time of flight here is 1.924 seconds. All right, as far as the velocity then at impact, I want the velocity at this time when the rock hits the ground, so it would be v of 1.924. So I'm just going to go back up and grab my v equation from my equations of motion. That would be 10, comma, negative 32 times 1.924 plus 10. So x component of the velocity is always 10. And I get negative 51.568 for the y component of the velocity. Notice that is falling. The y component is downward, which totally makes sense when that rock hits the ground. All right, a couple more questions about the same problem. The next question is a new one. It's not one that we asked in the one-dimensional situation because it didn't make sense, right? One-dimensional, it just went straight up and straight down. We can now, however, ask about the range. What is the horizontal distance the rock flies? So we now want to know, where is this rock actually landing? What x value do we have at this point where the rock lands on the ground? So I know it took 1.924 seconds to land. If I plug that 1.924 back into my position equation, the x value is going to give me this distance right here that it flew horizontally. So I'm looking for the x value at the time of flight. So let's see. X is just equal to 10t. If I plug in the time of flight that we just calculated, 1.924, I'm going to get 19.24, and that would be in feet. Finally, in E, I want the maximum height of the rock. This is going to be the maximum y value. Since, of course, y is measuring our heights. And again, the y value from our initial position equation was negative 16t squared plus 10t plus 40. And I know I can maximize anything by setting its derivative equal to 0. So it looks like t is negative 10 over negative 32, or about, actually I can put it exact, 0.3125. Now that doesn't tell me the maximum height, it tells me what time we reached that maximum height. So I'll plug that back into y. To actually find that maximum height. And I'm getting about 41.56 feet. So if I were to sketch my trajectory one more time, I now know a lot of stuff about it. Again, we started here at a height of 40. We have calculated the maximum height here is a y value of 41.56. And we also know when it occurs, right? This was t equals 0 when we started. This occurs at t equal to 0.3125. We know when the rock lands. The time of flight occurred at t equal 1.924. And we also know where the rock lands. The range was 19.24. So the calculations that we've done have given us a lot of information about that trajectory. right, let's try another problem here. In example 3, a cannon fires a ball from ground level. If the initial speed is 120 meters per second, at what angle should that cannonball be fired in order to hit a target 800 meters away? And I'm just going to read B as well. In B, if the initial angle is 25 degrees, at what speed should the ball be fired to hit a target 800 meters away? So if you specifically know where a projectile needs to land, I either need to tell you the initial speed or the initial angle, and you should be able to find the other one. So let's go ahead. Part A. Always helps me when I draw these. They specifically said that the ball was fired from ground level. So that means I'm going to start right here at the origin. And 0, 0 is my initial position. X naught, Y naught. Cannonball goes up and down. And here's my initial velocity vector. Now I don't know the angle, so let's just call this theta. But I do know the initial speed, the magnitude of the velocity vector was 120 meters per second. So I'm going to go ahead and say this is 120 cos theta, 120 sine theta. I can't simplify beyond that, since I don't know theta in this case. But that's my u naught and my v naught. Finally, I know I want to hit the target 800 meters away, so I know where this cannonball needs to land has an x value of 800. All right, let's start by writing the equation for r. And let's see, before I actually do that, let's just make the remark. The gravitational constant here, since we're working with meters and seconds, would be 9.8 meters per second squared. So for r, I'm going to get u naught, which is 120 cos theta, times t, plus x naught, but x naught is just 0. Negative 1/2 g. Half of 9.8 would be 4.9, so negative 4.9 t squared. Plus v naught times t. That would be 120 sine theta times t. Plus the y naught, which is 0. All right, we're now going to actually set up a system of two equations with two unknowns. And I'm going to do that by using this point where this cannonball has to land. I know when the ball lands, the x value is 800 at the same time as the y value is 0. So I'm going to set x equal to 800. And I'm going to set y equal to 0. All right, so I've got my system of equations. My two unknowns are t and theta. And ultimately, my goal is to solve for theta, right? Let's see. It's not a linear system, so my little app on my calculator is not going to help me this time. Instead, I think I'm going to go ahead and solve for t in this top equation. It's pretty easy solve. And then I'll substitute into the bottom equation. So t would be 800 over 120 cos theta. And I'm going to substitute that into here. Let's see, let's just reduce that fraction first. Keep our numbers as small as we can. Looks like 20/3. So I'm going to have, use a little more space here, negative 4.9 times 20 over 3 cos theta squared plus 120 sine theta times 20 over 3 cos theta equals 0. And again, let's just get a little bit of arithmetic done. We've got negative 4.9 times 20 squared divided by 3 squared, or 9. So that coefficient right now is negative 217.7, no, actually let's just keep it exact for the moment, negative 1960 over 9. Cos squared theta on the bottom. Plus 120 times 20 would give me 2400 over 3. And that would be sine theta over cos theta. And I think I'm actually going to leave it that way for now. I was thinking about writing tangent theta, but I think I'll leave it like that because I'd actually like to clear fractions in the next step. So let's go ahead and multiply everything through by this denominator, this 9 cos squared theta. Both sides. And that's going to give me negative 1960 plus, let's see, over here 3 would go into 9 3 times, and one of those cosines will cancel. So I'll get 7200 sine theta cos theta. Excuse me. All right. In order to solve this trig equation by hand, I'm going to need to get it down to just one trig function, which I'm going to do. But I will also say that at this stage, there are many times when you get down to a simplified equation that you look at it and say, gosh, I don't really think that there's anything I can do to get this done by hand, and it's probably true. So you can also just graph something like this at this point and get the numerical solution graphically. In this case, I think I can solve by hand, so just to stretch our trig muscles a little bit, let's go ahead and do that. I'm actually going to do this. I'm going to factor a 2 out of here. I'm going to make that 3600 times 2 sine theta cos theta, specifically so that I can take advantage of the double angle formula. 2 sine theta cos theta is sine 2 theta. And that's just a trig identity. But that's going to allow me to actually finish solving. So I'm going to have sine 2 theta equals 1960 divided by 3600. 2 theta is the inverse sine of that value. And let's go to degree mode. And I'll take the inverse sine. And I get just about 33 degrees, 32.986. I'm going to call it 33 degrees. Meaning theta itself is going to be 16.5 degrees. And that answers the question that I was asked, right? I wanted to know at what angle I should fire this cannonball at. I need to fire it at a 16.5 degree angle. All right, we're running a little long here, so I'm going to come back and do part B in the next video.